Okay, so we haven't seen each other in a while, so just want to do a little review of what we've done. So the whole point of our discussion so far is solving linear systems. That's kind of our entryway into thinking about a matrix. So you can think about solving linear systems without the use of a matrix. But it can get a little messy because there's a lot of symbols you need to keep track of. But as we're kind of going through solving systems, our goal is going to be to first focus on elimination. And then once we cannot eliminate anymore, then we think about substitution. And the word we used was back substitution. So this was kind of like once we've exhausted all of elimination, then we get a substitute back to get the solution. So we introduced the matrix as a tool that makes solving systems easier, which we call the augmented matrix of a system. It was comprised of a coefficient matrix, which consisted of the coefficients of the variables, and it was augmented with a column of the constants. So that was right. If you want to think about when you write the augment, right, this line are equal signs. So if you want to read out the system, your equal signs kind of where that line is. So the matrix, how it was comprised was that the rows of the matrix represented the equations in that order. So the first row would be the first equation, and the entries in the row in their respective columns were the coefficients of that variable. So the first column would be the first variable, second the second, etc. So you do have to kind of give yourself an ordering. So if it's like X, Y, Z, you kind of have to set which is the first variable, which is the second, which is the third. And then the thing you're augmenting with is this constant. Okay, so we talked about three types of operations on rows. The first type we had was type 1, which is swapping two rows. Second was type 2, which is multiplying a row by a constant. And the third was a type 3, which was adding a multiple of a row to another row. So all these three types, represent equivalencies that you can do in systems of equations. Right? You can always reorder the equations in a system. You can multiply both sides of an equation by a number and it won't change it. And the adding of a multiple of a row to another row was kind of like this. Equal things added to equal things give you another equal thing, which was also valid. So I kind of like to lump type 1 and type 2 into its own category as they're kind of like setup types. So when you're going ahead to eliminate, you might use these first two steps to set up. What are the setups? Maybe swapping two rows to put a favorable row in the first position. Type 2 might be used to give you a 1 in a favorable position, or if you have a row that's fully that has a common factor, you might want to divide out to simplify it a bit. And another good use of type 2s was to get rid of fractions, right? You can multiply by the GCD or LCM. LCM to get to clear the denominator. And then type 3 is the main thing that we're going to use to eliminate. So it's this adding a multiple of a row to another row. Okay, so we talked about an algorithm that can do this very reliably. You can tell a computer to do. There's some things that you can do yourself to make it a bit easier, like to pick out nice rows to use. So our algorithm in general is to look at our first row and swap it with a good row. So a good row is obvious. First of all, it needs to be not, you can't have a leading zero, because then you can't eliminate, because there's nothing to use to eliminate. And preferably you like plus or minus ones, because it makes elimination a lot easier. If you can't do that, if there is no plus or minus ones, and you don't want to do a type 2, then you have this formula which you can easily derive as a way to, it's really just algebra, as a way to derive how to eliminate variables. So this is what you do. You use row 1. So this should be row 1 here. You use row 1 to eliminate every other variable and every variable of each equation underneath it. So at the end, you'll have a column full of zeros except for the first entry. So once you have that, what makes an algorithm is that you can repeat this and then you can continue it until there's nothing more to do. So what is the, how do you repeat it? Well, we can reduce the system by 1 in each dimension by ignoring the first row and first column. So we've already used the first row in our elimination, so we don't need to do that again. And we've eliminated our first variable, so we can continue on to the next column. So you just repeat it on this one less dimension system, and then continue until you are finished. So this will give you a system that's in like a triangle form-like system, but we talked about something called row echelon form last time, which was an especially nice form of a system, which was what? Can someone say what makes row echelon special or different than a triangle system? Yeah, so 0 is kind of, that's a part of it. So it's kind of like a triangular part.
So the first non-zero entry is 1.
Correct.
All the rows, like if there is a row full of zeros at the bottom, and then the leading rows have zeros.
Yeah. So you have this kind of like increasing in the system as you go further down. There'll be more and more zeros leading, but and then what makes a row echelon is that the first non-entry is 1. Non-zero entry is 1, or leading coefficient's good. So to make it to row echelon form, if you don't have leading ones, you can easily do a type 2 to just make it 1. So you just divide each row by its leading coefficient, and this gives you 1. So we'll see kind of more today why these leading ones are nice. But at the end of the day, when something is in row echelon form, all you have to do is back substitute. And that's the kind of nice thing about this form, is that it's easy to back substitute. Okay, you have a question about problem we did last time? Oh, this is about the free variables?
Yeah, about the 4 variables, I think, with the W as well. Yeah, at the 4x4.
Or this one?
The solution was x equals 1 and the rest 0, right? But at the very top, if you scroll to the very top, wouldn't that not satisfy the first system, like a negative y minus x plus w?
What was
oh wait, I'm sorry. No, never mind. I didn't see that there wasn't an x. Sorry.
Okay.
Never mind. Yeah.
So it's trivially satisfies that. Okay. Cool.
Yeah. Thank you. Sorry.
Yeah. So does anybody have any questions on just kind of this general scheme that we've kind of been doing? I just want to kind of do a quick review of like kind of what we've done. So in your homework, hopefully use some of these techniques. And essentially in the second homework, you'll be doing this again. But we're introducing, row echelon, and today we'll talk about reduced row echelon, which is even nicer form of the system. Okay, so no questions. Just want to get some definitions. So we've talked about this, but I'm not sure if I have exactly defined it. But I think if you've done the homework, I think you've kind of figured out what the definition is. But a consistent versus inconsistent system. So can someone say what the definition is? If you've done the homework, you probably should know. What does consistent mean?
Has a solution.
Yeah, consistent is has a solution. And then inconsistent does not. Yeah, sorry about that. I must have missed that. So, and yeah, that's good. It has at least one. So there could be infinite solutions, but it has at least one. Yeah, sorry for not defining that last time. Okay, so here's another type of system. Over versus under determined. So this is based on the dimension of the system. So if you have, so remember the dimension of the system is m by n. Can someone say what the m represents? What's your first dimension in a, what's your first coordinate in the dimension? Is the row. And if, in terms of equations and variables, which is it?
Variable.
Other one, it's equation. So the rows represent equations. The n is that's the variable for the columns. Okay, so if something is called overdetermined, you could think of it as there's too many equations. Right? If you think about the solution of a system depends on your equations that you have. If you have too many equations, you may have I'm not sure if you found, if you in your homework, I'm not sure if you had any of these, but at least in your second homework you will, is that oftentimes you can eliminate rows completely. So yes, if you have too many equations that determine the solution. So it's the idea is that like at least one of those equations is like negligible. Yeah. So, and then underdetermined is there's not enough equations. Or you can say too many variables. Yeah. I like to just think of it as equations, not enough equations. So this is usually m less than n. So I think the interesting types of systems, which will work more in today, is underdetermined. This is kind of more interesting. Oops. Usually these will be infinite. Usually infinite number of solutions. And under is often inconsistent. Not always, often inconsistent. I should say not usually, but often. And here's kind of a way to think about it. Like if you have 10 lines in a plane and you want to find the solution. So you think after 2 lines becomes more and more restricted. This is interesting. I find these to be kind of interesting systems. And this is m is less than n. Sorry, my computer's a bit laggy, so the handwriting is not the best right now. So if you have like 10 lines, it's pretty restrictive on what the line should be in order for there to be a solution, right? Right. If there is a solution, that means all the lines intersect at one point. So the restriction on each line subsequent is kind of more likely than not it's going to be inconsistent, because if there's one line that doesn't cross through all of them, then it's immediately inconsistent. So I think even just the harder problems is like, you know, when there's not a lot of information to work with, it's kind of harder to figure out a solution, or at least harder to express a solution. But hopefully today we kind of talk about, so in the cases where there are infinite solutions, we'll talk about, it's called free variables. So let's do an example. Actually, we did last time an example, but we already did that one. So let's do a different example. I'll do a very boring one, and then we'll just talk about why we care about free variables. Oh, I didn't do what if m is equal to n? We usually call this a square system. So there's just the right amount of equations and the right amount of variables. And these are the nicest kind of systems. And we'll see why later, but we usually call this square. So it's usually like, we usually express it as n by n. Right? If m is equal to n, just replace one of them. Let's talk about free variables. So I'm going to give you a very boring system. And you tell me what the answer is. What's the solution to this system? So what do you mean x, y? I would agree with you, like that. It's a way you can talk about it, like, but what do you mean? 0, 0 is a solution, but it's not the only solution. Yeah, y equals y. Okay, what does that mean? It means everything, yeah. This is like the only case where we have like everything, right? So I would, in terms of notation for expressing a solution, we want to avoid using x and y. And on other variables, because usually these represent like unknowns. Right, but we're solving for it, so we do know it, right? So when we have an infinite number of solutions like this, how do we express this? So yes, this is like a solution, x, y, where x and y are anything. So I'll put this in quotes because we're going to give a better explanation of that. So we're going to use Greek letters. So use instead free variables alpha and beta. So these will represent that they're free to be any real number. Free to be any real number. So how would we express the solution in like a nice way, which a way that I would want to either express it would be any numbers alpha and beta, and then we're going to use these notations. It's kind of an upside down A. And so this means for all. For all what? For all alpha beta. These can be any number. And what kinds of numbers can they be? Well, we only care about the real number, so we don't want i's. So this symbol means in, and this symbol means the real numbers. And again, that's as opposed to like imaginary numbers. So that's how you express the solution. So what does this mean is that in the solution, x can be anything. And y can be anything. Hey, any questions on that notation? So if we're dealing with a kind of infinite amount of solutions, we're going to use like alpha, beta. Sometimes we might use gamma if there's a third, or delta if there's a fourth. But just to avoid using x, y, z, because that kind of represents something unknown, but we're actually solving for it. Okay, so any questions on that? Okay, so let's do another example where we have free variables, one that's pretty easy too. X plus y is equal to 1, and 0x plus y is equal to y. Okay, so what's the solution here? Let's start with which of these equations is kind of nonsense? Not nonsense, but boring, let's say. Yeah, the second one is just y equals y, right? So the idea is in the solution, y can be anything. So then you look at x, or you look at the first equation. All right, so what is the solution in the first equation? X equals 1 minus y. Cool. Okay, so if we want to use this notion of free variables, first of all, x can be anything, right? Or so let's start with y. Y can be anything, right? So let's let alpha equal y. Can x be anything? Yes and no, right? What's the no part of it? X can be anything in the sense of like it can be any real number, but there's some restriction. It doesn't have to be less than 1, right? What if alpha could be negative, right? It's dependent on y, yeah. X is dependent on y. So really, x is not free. because it's dependent. So what are the solutions? Well, X is dependent on Y. Or not Y plus 1, but right, 1 minus Y. And for any alpha in the reals. Does that make sense? So there is a free variable here, but there's not two free variables. And the other one we had was that both variables were free. Alpha was free to be anything, and beta was free to be anything. But in this case, alpha could be anything, but there's a restriction on the other coordinate. Question, did Y have to be alpha? What if let X equal alpha? What would Y equal? Like what, for Y equals 1 minus X. Y could equal, or the second coordinate could be 1 minus alpha. So it doesn't matter like which of the variables want to be free, as long as the other one we make dependent. So these are both valid solutions. Everyone see the difference between the two? And by difference, I mean, do you see how they're the same? Yeah, the idea is that you can make either one of them the free variable. You might always want to make X the free variable because it comes first, and then kind of work from there in terms of how you count the number of free variables. But these are both valid. In this case, X, I made X the alpha. Right, if you solve for Y, you get 1 minus X. And then if you solve for X here, you get 1 minus Y. So if you want to think about it as like functions, in this case, you're treating X as a function of Y. In this case, you're treating Y as a function of X. So just kind of different perspectives. Any questions on that? Once you have they're both lines in either case. We're probably more comfortable with this one. Because X is the variable and then Y is the dependent variable. But usually Y is when we do math class, Y is usually dependent variable. Okay, is that good? Okay, so let's add a dimension of complexity. Just one dimension. X plus 2y, we're going to add another variable, z, is equal to 1, and then negative x minus y minus z is equal to 0. Okay, first, let's just review matrices. Can we put this in a matrix? What is the matrix form? Someone give me the first row.
1, 2, 1, 1.
1, 2, 1, 1. And what's the second row?
-1, -1, -1, 0.
And what would our first operation be to eliminate the first variable?
Add rows 1 and 2.
Yeah. So we're going to change row 2 by adding row 1 to it. So we didn't do anything to row 1. And to row 2, we're doing 0, 1, 0, 1. Okay. Is this in row echelon form? Yes, it is. It's not high school, yes. Yeah, we have leading ones. And there's more leading zeros in the second equation than there are in the first. Okay. So now let's think about substitution. How do you solve this now by substitution?
We know that y is 1 now.
Right, we know that y is equal to 1. So what does that imply for equation 1? If you plug in 1, you get x plus 2 plus z is equal to 1. And you get x plus z is equal to -1. Okay, so the idea is in our system right now that we've simplified was x plus z is equal to -1, and we have y is equal to 1. So how do
You
you...
forgot that negative sign.
Oh, -1, thank you. So in our system, our solution system, the second coordinate always has to be 1, right? But now in the first and third coordinates, there is restriction. So let's think about in free variables. Why don't we solve for x? Because we like maybe our first variable to be free. Sorry, why don't we solve for z, because that would make the x the free variable. So we have z is equal to -1 minus x. So the idea, so let's think about this abstractly as just a linear system. Forget about the second variable. This is saying that there is kind of a line looking thing of z equals -1 minus x going on in our solution. So what is the restriction on solutions that, well, let's say x can be anything. What is the restriction on the third variable if x is whatever you want it to be? -1 minus alpha. So let's make that solution. So x can be whatever you want to be, as long as the third coordinate is -1 minus alpha. So x is free to be anything, as long as the third coordinate is dependent on alpha. So that's why it's a function of alpha. So for any alpha in R, this is a solution. Yeah, so the point is just, that's just nicer notation because x, y, z, etc. look like things that you don't know. Whereas if we use something that's different than that, like alpha, beta, whatever, it's saying that these are things that we do know. So x, y, z is usually a variable that we don't know, but we're saying these are things that we do know. So it's just notation. Like we don't want to use a variable that we're looking for in our solution. Okay.
So if we wanted z to be free, then we would solve for x.
Yeah. So let's give an example of a point on this in the solution. We wanted to be this whole thing to be free. So it'd be like -4, right? let's say if alpha is equal to -4. So you can give me any alpha. So if, for instance, if alpha is equal to -4, then -4, 1, -1 minus -4, or -4, 1, 3 is in the solution set. So you could choose alpha to be whatever. It could be pi, it could be 1/10,000, right? So whatever you choose for alpha, z is dependent on it. So then you plug that alpha into where it is in the z coordinate, and you get a thing in the solution. Okay, questions on this? Okay, so I'm going to introduce, before doing an even more complicated system, I'm going to introduce another algorithm to make this even easier, called Gauss Jordan Elimination. So what this does is puts a matrix into what's called reduced row echelon form. And let's define that. So reduced row echelon form is in row echelon form with some extra qualities. And so all entries above, I'll put in quotes and below because that's just required for row echelon, are 0, or above the leading ones are 0. Okay, so in row echelon form, we have these leading ones, right? But if we want to put something into reduced row echelon form, we also have to eliminate all entries above each leading one. So we're going to do this by kind of an example, but the general idea is called upward elimination. So when we've been eliminating, we've always used the first row and we're eliminating downward. So the idea is that once we fully eliminated, we can actually do even more by eliminating upward instead. So let's take our row echelon form and say what our reduced row echelon form would be. So 1, 2, 1, 1, 0, 1. So here's the general algorithm for reduced row echelon form. So, okay, we've put it in row echelon form, and now we're going to use the last row. That's non-zero. And eliminate above the leading one. So the idea is that if we want this into reduced row echelon form, can someone tell me which entry needs to be 0 based on this definition? Which entry would you want to make 0? Yes, the A12 or this one, A12. Now, I know we've been always eliminating downwards, but can someone tell me what can you do to row 1? What can you multiply row 2 by such that we can add it to row 1, it eliminates that entry? Good, yeah, -2 times row 2 does that. Right, And what's nice about row echelon form is that since this is a 1, this is a very easy calculation, right? It's always going to be negative of this entry in row echelon form. In row echelon form, that is always the negative of the entry above it. Okay, so let's do that. Okay, and now what's nice about this is that, can someone say, does this entry change?
Both the first and the third wouldn't change.
Right, because of leading zeros, first column does not change. We wouldn't want it to change also, right? Because this was nicely put into a row echelon form, and if it were to change, it would ruin the row echelon form. And yes, as a consequence, this also does not change. Yeah, so let's say what that gives us. We get 1. Now this changes to a 0, and you're correct. Third also doesn't change. Now, what does the last entry become? What would this entry be? -1, correct. Right, so remember this is like 1 minus or plus -2 times 1. Okay, so what is so nice about reduced row echelon form is that you can give me the solution just based on what it looks like here. What we can do is, here's a neat little trick. So first we can draw a little box of where there's a diagonal of 1s. Anything that's left over are free variables. Yes, in the front. It has to be in the front. So this will always be 1 by our construction. So if you draw this box, these will be your they're not free variables, and then the leftovers are free variables. So the idea is that you can automatically make a solution of, if you just solve for it, you get -1 minus alpha 1 alpha. So this leftover is free. And then you're solving for, and we're solving for this first row. The idea is that you can see your free variables very easily when it's in reduced row echelon form. Okay, so this was our solution from last time, or we did a different way. If we let this be the free variable, it would have been alpha 1, and then -1 minus alpha. Okay, so let's do one more step of complication. And this is pretty much, we'll finish 1.2. x1 plus x2 plus x3. We'll add a 4th variable. It's 4. It's equal to 2. x1 plus x2 minus x3 minus x4 is equal to 3. x1 plus x2 plus 2x3 plus 2x4 is equal to 1. Okay, so what's so nice with the matrix is that we can just not have to deal with all these x1, x2, x blas, right? So we can just put it in the matrix. So let's do it. So their first row is 1, 1, 1, 1, 2, 1, 1, -1, -1, 3, 1, 1, 2, 2, 1. Okay, everyone agree with that? That is the augmented matrix. Okay. Now let's use Gauss Jordan elimination. And put this into reduced row echelon form. Okay, so the first step is to just put into row echelon form. So give me a step that would do that. What would your first step be? Put this in row echelon form. Good, yeah, so I can change row 2 by doing row 2 minus row 1. And at the same time, I can do row 3 to row 3 minus row 1. So let's do that. So first row does not change. So if we subtract the 0, 0, so -1 minus 1 is -2, -2, 3 minus 2 is 1. Okay, so then we have 0, 0. Okay, 2 minus 1 is 1, 2 minus 1 is 1, 1 minus 2 is -1. Okay, what's next? So in our algorithm, we've reduced the system. How do you continue? So first of all, there's nothing to do here. So yeah, I do like row swapping because you don't have to deal with fractions to avoid fractions. So let's do that. Negative. Good. So now what is an operation to eliminate? So remember, let's think about it in type 3s because we can just do that in one step. So I think what you mean is to do row 3 to row 3 plus 2 row 2. Yeah. Okay. Again, you can do a type 2 and then add, but I think it's better to do it all in one step. Okay, so what do we get? And then what do we get here is okay, so you might be scratching your head about this, but yeah, it's inconsistent. But how can we put this into row echelon form? Or reduced row echelon form? Yeah, you can do that step. So row 1 minus row 2. Yeah, can you explain why this is inconsistent? what does the third row say? Yeah, because 0 equals -1. So there is no solution. Okay, so we had a 0 solution. Oops. All right, let's any questions on that?
Yeah, why do we do that extra step of row 1 minus row 2?
It's just to put it into a reduced echelon form. We have these leading ones, but this was not a 1. Oh, so that needed to be 0. No, I just made this up, but I'm gonna do another one, and hopefully we'll have a solution. Does that make sense? For reduced form, these leading ones need to be a 0. That's just our definition of reduced row echelon form. All entries above the leading ones are 0.
Oh, okay, yeah. I'm sorry, I kind of like forgot the definition.
That's okay. Yeah. All right, let's do another example, which hopefully have a good one. All right, so let's do x plus y plus z plus w is equal to 1. Negative x minus y minus z plus w is equal to 1. And let's do x minus 2y minus z plus 4w is equal to 0. Okay, so let's put this one into matrix form. So we have 1, 1, 1, 1, 1, -1, -1, -1, 1, 1, and 1, -2, -1, 4, 0. Okay, so let's, what's our first step here? This will be our last example, and then we'll be finished. Yeah, so we do row 2 plus row 1, and then what do we do to row 3?
Row 3 minus R1.
Yeah. So we get 1, 1, 1, 1, 1, 0, 0, 0, 2, 2, and then we get 0, -3, -2, 3, -1. Okay, cool. So now what? So we reduce the system by 1 row, 1 column. And how do we continue? Yes, swap. So let's do a row 2, row 3 swap. 1, 1, 1, 1, 1, 0, -3, -2, 3, 1, and then 0, 0, 0, 2, 2. Okay, so what do we do now? Is this in row echelon form? No. How do we make it to row echelon form? Yes, we can divide the second row by -3. And then what do you do to the third row? Right, divide by 2. 1, 1, 1, 1, 1. So 0, 1, 2/3, -1, 1/3. And this is 0, 0, 0, 1, 1. Okay, so someone say what entries need to be 0. So now this is in row echelon form. What entries need to be 0 for this to be in reduced row echelon form? A1, 2. Any others? Let's call it A2, 4. And what else? It's okay. And A1, 4. Right, both of them, because they're both entries above 1. Okay, so I won't finish it today since we're out of time, but your first step in your algorithm would be first you eliminate, so you're using the last row to eliminate upward because you're kind of reversing the step of the Gaussian elimination. So row 1 to row 1 minus row 3, and row 1 to row 2 to row 2 minus row 3. So that eliminates the zeros here. Oh, sorry, plus. This would be plus 0, and this would be 4/3. And then the last step would be row 1 to row 1 minus row 2. So 1 minus 2/3 is 1/3. So the idea is that these will be our free variables of alpha and beta. And then you solve. So next time, maybe I'll just express that solution. Oh, sorry, no, not this one, because you can actually solve for it. But this will be your free variable. Okay, so I'll stop recording now.